we have four and a roadmap of what I'm going to try to do. So we have seen the basic idea of prediction, classification, and then we saw local averaging ideas like Nadaria-Watson, like KNNs, partitioning estimators. Those are sort of non-parametric classifiers. And then we looked at this idea of empirical risk minimization, and that like directly attacks risk, minimizing the risk using so let's say let me just mention like basic decision theoretic. So this is what we have seen: decision theoretic formulation of prediction. Prediction, say optimal Bayes rule, stuff like that. So like local averaging, these are non-parametric parametric like approaches, which is and then we saw like empirical risk minimization. So examples of this are like usual like linear regression and linear methods of classification like logistic regression. And softmax regression. So these are all parametric approaches. So they're ERMs, empirical risk minimizers, with a parametric form for the function. So you can have empirical risk minimizations with non-parametric families of functions. But so far we have seen parametric families. What I want to do is like cover like a subset of these topics in the next 4 lectures. So the first thing is you've seen like regularization error problems, and there was a question on Campus Wire of what regularization do. Okay, so this is something that I hopefully will try to answer, and we can get a nice answer in the context of ridge regression. And you're going to do a lot of the work yourself, let's say in the homework problems, ridge regression. So depending on how it goes, we might get to it a little bit today. The other thing that I want to do is like talk about some non-linear parametric models. For example, neural networks are examples of parametric models that are non-linear. And there's another way of constructing non-linear parametric models. So the neural networks lead to deep learning and like a lot of like cool stuff, like convolutional neural networks for visions and other stuff that I may talk about later. And then there are other approaches like the approach using feature maps, basis functions. This leads to the kernel trick, leads to kernel methods. And kernel methods are not like more general than parametric models. They can be non-parametric. This requires some theory, RKHS theory, which we won't cover. So depending on how it goes, that's the thing. So I'm going to talk about neural networks today. So non-linear parametric models. Then talk about like regularization maybe after that. And at some point we come back to these feature maps, hopefully. But what the other thing that I want to cover is here. So we're going to see. So bigram language models, and then like a few steps, and then you get GPT, and then ChatGPT like is like almost there. So depending on how things go, I might talk about this. The thing that I probably won't be able to cover is like ensemble methods, random forest gradient boosting. But depending on how it goes, I might say a few words about that, but you can learn that yourself. These are ideas based on subsampling or like resampling data. And so the like random forest is like that. Gradient boosting is it's very relevant to what we talked about. It's like a gradient descent in the space of functions. And so these are more classical ideas, but they work really well. So the issue is that like modern sort of machine learning has focused on deep learning neural networks. These more classical ideas, however, work very well in like tabular settings. So the classical settings that statisticians work with, they're sort of the state of the art. So even kernel methods, these SVMs, and in this course, hopefully by the end of this course, you get a sense that you don't have to like do like deep learning, like to like do classification based on 2 features. So there's a limit to the problem. There's a base limit, and oftentimes you can approach it like in simple cases by a very simple procedure. So you don't have to like put a very complicated model. So the thing that I want to emphasize is sort of the interplay between complexity of the model and the classification problem. That the underlying thing is hard to get to. We will see a little bit of that in what regularization do, but you generally want to balance complexity of the model versus the sample size, how many data you have and how many features you have. Is the plan sort of okay? Right. Okay. So I'm going to talk about neural networks a little bit. So start with that. So why would you care about these guys? What are neural networks? Let me ask you guys. What are neural networks? Let me motivate by this. So if you recall, so ERM formulation of logistic regression. So we started with something like probability of y before actually ERM, just the logistic regression. We started with something like this, that's the logistic regression. And then estimated parameter turns out to be like this, argmax or argmin, like an empirical loss, like yi theta transpose x. If this is log loss, or it would be like yis theta transpose xi, if this is like BCE. So you can see that you can absorb part of the classifier into the loss. So this one, if you look at it, you see there's this linear function there, and this is the source, or this linear function here, and this is the source of the linear decision boundary. So when you look at the decision boundary, we saw like the decision boundary between the 2 classes, the base classifier, the way that it like classifies the points is like to like the 2 sides of a line or a hyperplane in general. So if you have something like a setting in which the data is like one class is here and this class is there, maybe a little bit of overlap here. This makes sense to classify using a decision boundary which is linear. So there is some sort of a function or a linear function that separates the 2 classes. So sometimes these data are called linear separable if they perfectly separate. So if there's like perfect separation, so one class is here exactly, the other class is here. This is called perfect, like linearly separable data. Even if they're not perfectly linearly separable, they're almost linearly separable. So logistic regression for this case makes sense. In higher dimensions, this would be a hyperplane. But what if if I look at the data and one class is like this, and the other class is like this, right? So a linear boundary we saw like is not a good choice. So I can try to do like this. That's not going to work. I can try to do this. Everything is to one side. Try to do this. Like some are better than the others, but clearly there is some sort of a non-linear decision boundary here. So it's like I want this side of this curve to be like one class, the other side to be another class. So this cannot be achieved by logistic regression. What is the solution? I can just replace this with some nonlinear function. Okay, I might have some sort of a like f theta of x here, which is parameterized by some parameters. That would be sorry, not f here, sigma. That would be like replacing this with f theta, of xi, and if I call this thing g theta of x, this would be now, oh, sorry. So this would be f theta of xi. So I would have like, once I go through this calculation, if I leave the sigma, the MLE would still look like that with the log loss, but now I have a generic function here rather than a linear function. Yes.
Then just looking at your data, what would be the training error that's acceptable to consider something linearly separable, like you're saying? Or is it just looking at it? Like, is there a specific like
margin of so the thing is, first, you can't usually look at the data. So it will specifically take like two features or so that we can look at the data. But in general, like if you have more than one feature, this space would be like maybe 10-dimensional, 20-dimensional, 50-dimensional, and it's hard to visualize. People try to like project down, so that's another topic that we unfortunately don't cover. So do dimensional reduction, try to reduce it to 2 dimensions so that you can visualize, but you lose the picture in high dimension. So it's hard to visualize what the data looks like in high dimension. So that's why you don't do things blindly. The thing that people do in practice is that you apply different methods, and then you measure the performance either by training, which is bias, as you hopefully probably now understand, or most likely with the test data, or what they call validation data, which what I call test is usually called validation. So you split your data into training and validation, and then just try different models and validate. So if you do like a linear model like logistic regression, and then you do a more complicated model, and the like validation area is like slightly better, then you'd maybe say, I'm not going to go with that like more complicated one. But if it's like a significantly bigger like jump, then you would probably like guess that you're in this situation. Okay. I'm going to show you an example shortly. Like the breast cancer data, we're going to fit a nonlinear model as well as like the logistic regression. The performance is not that different in that case. So it's up to you in that case whether you want to go with the linear model. So the linear case is simple. So it's interpretable. So statisticians prefer logistic regression with linear boundary if it's possible, because then you can interpret exactly like how each like feature like contributes to the classification. So I can tell you, for example, exactly that the log odds are theta transpose times x, and so this particular feature, if I like add like a bit to it, this contributes this much to the log odds. So I can like, for example, if like one of them is age, if age is like multiplied by 2, the log odds of like cancer or something else like goes up by that much. So there's exact sort of like easy interpretation of the model parameters. But that being said, in some cases there is like a gap in performance. So if there's a huge gap, then you would prefer the more complicated. It's not an easy like problem. So it's the problem of model selection, which is always tricky. So the question that you ask, if you want to like put a name on it, it's like statistician would call model selection. Among the class of models that you can consider, linear models, like nonlinear models, non-parametric models, neural networks with like 50 million parameters, or like 50 billion parameters, or like 100 layers or 2 layers, which one should I choose? So there's a trade-off. So but yeah, so we'll see some examples. Good question. Any other questions? But let's say I want to try out something. Okay, so if I want to try out something, I need to find. I don't necessarily need non like parametric models. You already have non-linear models. So if you remember, if you go back and look at the decision boundaries that you derived for this for the breast cancer data, it was non-linear. Okay, so this has the ability to fit non-linear decision boundaries. It's non-parametric. The issue like finding the right bandwidth, finding the right kernel. If the kernel is not appropriate, changing the bandwidth is not going to change like that much. For example, if the data are different on different scales, like your midterm exam, if you don't properly normalize, you don't get very good performance. So So there are issues there. So it's not universally applicable. So you have to like construct the kernel properly. You have to choose the bandwidth properly. But nevertheless, those are very powerful methods. They don't have to have single parametric model. There's like basically zero training except for picking the bandwidth. And so you already have something in your disposal at your disposal. But let's say I want to like force myself to look at neural networks and look at parametric, like nonlinear models that are parameterized by a parameter, and I want to optimize the loss to get the best model in that class. So neural networks are examples of these parametric models. So it's like a neural network is really a map, a nonlinear parametric map. So if theta maps x to, say this in RD, to some, let's say in our case, to something real, like in multi-class classification, or some other setting to a vector. So let's say this maps things to f theta of x. How are these things constructed? So this is the general like neural net. How is it constructed? Usually, if anyone knows how they're constructed. What is a simple neural network? So you start from some sort of a linear map. So if I want to construct a linear map from RD to R, what would it look like? RD to R. X goes in. What is the general linear map from RD to R? If you recall, a general linear map can be written like that, theta transpose x for some theta. So these are the functions that look like that. So we're not achieving anything at this point. So this is a general linear map from RD to R. Now, if I want to like have a nonlinear, like linear map from RD to, let's say, H1, R H1, this is something not other than 1. So what would be a general linear map here? So X goes in. So D-dimensional vector goes in, H1 dimensional vector comes out. How can I represent something like that? Remember softmax business? There was a linear function from RD to RC. How would you describe it? So let's say R2. I want to find a linear map from R2 to R3. What would it look like? X is like X1, X2. If you involve softmax, things would not be linear. I want a linear map first. Softmax is a nonlinear operation. You can put a softmax here. Actually, softmax has like the same input dimension as the output dimension, but things would be nonlinear. What is the basic, like the linear model from, like a linear model from input to the output three-dimensional case? X plus B. This is an affine map, it's fine, right? Like in ML terminology, this is a linear map, yes, but not the most general one. I can do more. So this is like saying, first, it's not going to be from R2 to R3. This is going to be from R2 to R2, because if I add an intercept, like this is two-dimensional. If I add a two-dimensional vector to it, it's going to be two-dimensional. I want to go from this to this.
Multiplied by base matrix.
Okay, so that's the thing I'm trying to. There exists a matrix 2 by 3, such that if I multiply by this, I get the output, and this is the general form of a linear map. So the linear map from R2 to R3 is like a matrix multiplied by X. That's how you construct a general linear map. You remember. So intuitively, this is just theta 1, 1, x1 plus theta 1, 2, x2 theta 1, theta 2, 1, x1 plus theta 2, 2x2, theta 3, 1, x1 plus theta 3, 2, x2. So all of these are linear functions, and collectively they form a linear map. So sometimes people, like, as I mentioned, so they would like write something like that. So this is like theta 1, 1 from x1, x2 to the first. This is theta 1, 2. So that's theta 1, 1, x1 plus theta 1, 2, x2. And then you have similar thing here, similar thing here. Okay. So these are basically these numbers are you put on this, but like and under the hood, this is just a matrix multiplication. So x goes in, multiplied by theta, you get theta x. That's a linear map. Sometimes we, instead of theta, I'm gonna just, like with the convention of neural net, there's a w and b. So I'm gonna write wx plus b. I include like an intercept as well, or like the bias term. So this is going to be 2 by 1. This is going to be 2 by 3. This, sorry, 3 by 2. This is going to be 3 by 1. So this is the general form of a linear map, or an affine map. Mathematicians would call it affine. Machine learning people will call it a linear map. Okay, so at this point we haven't achieved anything, but this is the most general linear function that they can have. So suppose I want to construct more complicated functions, like in the hope that I can get something like nice here, like complicated. I might imagine trying to cascade these. So the neural net idea is to try to compose functions. So this is one function. So if, let's call this F1, it has base, I'm gonna not write it. This is gonna be W 1x plus B. W1, B1. So, and I have another one, which is maybe F2. This would be W2x plus B2. So F2 of x would be W2x plus B2. What I might think is, okay, maybe this is, let's say 2 by 1 goes to 3 by 2. This takes like 3 by 1 and then maybe maps it to 1. Okay, so dimension like 1 by 1. So this would be 3 by, so 1 by 3. And this is going to be 1 by 1. So then I can cascade these two. Like I take the like output of this and feed it into this guy. So this is by like mathematically would be like a composition. But now this is like goes from like R2 to R3, and from R3 goes to R. So now I have a more complicated function, hopefully. I can call this g of x. And this g of x is going to be my model. So data goes in, passes through the first sort of layer, passes through the second layer. There's like an invariant output. So this g is going to be from R2 to R. Except that this is not gonna, it's gonna do something, but it's not gonna be what I want. This is still gonna be a linear map. Why? Why would it be a linear map? Is it like setting clear? So I have like 2 by 1 vector goes in. Here W1, B1. So this is X. This gives me W1X plus B1. And then I feed it through this guy, which is W2, B2. What this does is that let's call this Z. Takes W2 Z plus B2. Now that's my output. Okay, it's going to be a function of X. So why this is not that interesting? Can I write it in terms of X? W1 or W2. So we want to write the output. W2Z plus B2 would be W2 W1X plus B1 plus B2. Okay, if I expand, I get this plus W2 B1 B2. So this function G that I have is really W2 W1X plus W2 B1 plus B2. What is the problem with this? You get like something nonlinear. We did not. Why did we not get a nonlinear function? Can you like tell me why this is not a nonlinear function as a function of x? It's linear. So this I can call another like weight. So call this W3, call this B2. So this is really W3x plus B2. So composing two linear functions, or let's say affine functions, gives me another affine function. So I can't leave the space of linear functions by just composing linear functions. There's a tiny thing that we achieved here. So not here, but this parameter is like a factorization of two parameters. Sometimes this factorization helps reduce the parameter space, but that's a different story. We come back later to. But the class of functions that I got is not going to be like things are still going to be linear. So if you look at if you have this function, like go through this trouble of constructing this family, and then you try. Now G has like W1, D1, W2, D2. These are all the parameters that it has. Plug it into the log loss and try to optimize. You do a lot of work, but in the end, the decision boundary is still going to be linear. Okay, so you really didn't achieve anything by just going through this complication. This is going to be 1 by 2. This is going to be 1 by 1. You could have started with just a 1 by 2 vector. Like with these simple parameters, I could just call this and then optimize over that. Still would get similar type of result in this case. In more complicated cases, this factorization is a low rank factorization. It would help, but that's a different story. So the idea of neural networks is this clear, sort of? The idea of neural networks is we do this composition, but we add like a tiny bit of modification. So before feeding the output of this to the next layer, I'm going to apply an element-wise nonlinearity. Okay, so this output of this layer is 3 by 1. Before passing it to the next linear layer, I'm just going to apply like a univariate nonlinear function to every coordinate. So what I'm going to do is, the way I'm going to write it is x goes in W1 x plus B1, or sorry, W1 and B1. This would be W1 x plus B1. I pass it through a nonlinearity, which we call like either sigma or like, let me call this rho. And then I pass it through the next layer, which is W2 B2. That would be, so if I call this Z now, whatever is here is called Z. So this thing is Z. Let's call this Z. I pass Z, so Z would be, yes, let's not introduce another. So Z would be, I'm going to write it as rho W1x plus B1. This is really a pointwise operation. So rho is from R to R, and this is a 3 by 1 vector. I'm going to apply coordinate wise. So coordinate wise. coordinates. Y is application. Application of a nonlinear function. Right. And then I'm going to pass this through. And so this gives me W2 Z plus B2. Okay. And I can continue, like, pass this through a nonlinear, a component-wise nonlinearity, passes through another linear layer and go on. Okay. As much as I want. So these things would be called neural networks. So neural networks are basically a combination of linear maps, element-wise nonlinearity and composition of these operations. So you interleave composition of nonlinearity and linear maps. And then the resulting function, just adding this here, it would make things nonlinear. So now you're outside class of linear functions. We can visualize that rather easily. But basically that's what a neural network is. So if you want to write it, it's just sometimes this part, it would be just one. So like in the terminology of neural net, this would be one layer. So this is now a nonlinear map. So I'm going to call this F1 of X. So that would be Z. So the output at this stage is going to be called like a hidden layer. So the output of this is called a hidden layer. And then this is going to be passed through this guy, which is another. This is in this case linear layer, but if I sort of move to say this and then pass through another nonlinearity, this is like a second layer. Okay, so this would be the second hidden layer. So whatever is here is hidden layer, first hidden layer, second hidden layer. If it's in between layers, it's hidden layer. At the end of the things, that would be the output layer. The first thing is called the input layer. So input layer, hidden layer, and at the end, you cascade a bunch of these, and at the end, so you have the output. It's called output layer. Okay. So usually you see these people when they draw it, they have these, they really like to have like, let's say from 2 to 3, they do these connections. These are just those weights that we saw. These are exactly sort of, each one would have, like, you'd have, basically you have 2 times 3 number of weights. And so this one would be a linear combination of these 2, and so on. And then there's a nonlinearity, which is usually like implicit. So this node, the nonlinearity assumed that it's applied. So this node takes like rho of theta 1 x1 plus theta 1 2 of x2. Theta 1 2. And then I can go from this, for example, to 4 nodes here, whatever dimension I want. Each one, again, we have a linear map here. And so on. I can go back to 3, or I can go back to 2. You can be creative here. So I'm not going to write everything, but just something like that. And then at this point, I'm going to combine them into a single. So there's going to be another, and that's going to be my output. Okay, so this is now has one input layer, one hidden layer here, another hidden layer here, hidden layer. This is the output layer. So at each point, this is a linear map, and then element-wise nonlinearity is implicit at every point. If I don't apply a nonlinearity, it's fine, but this collapses into a linear map. It's just that sometimes, for example, if you go from like 10 to 2 and back to, let's say, for example, 5, this is like a map from R10 to R2, and then back to 5 is a little bit too big here. So this is 2, let's say this is 5. If I apply nonlinearity, it's a genuine neural network. If I don't apply it, it's just a combination of two linear math. But the matrices would be like with your product so W1, let's say W2, W1 would be the other way around. So with the W1, I'm going to ignore the bias, the intercepts. So the output will be W2, W1X. And so this is going to be 10 by 1. This is going to be 2 by 10. This is going to be 5 by 2. So this is another general 5 by 10. It's another map. So this is another matrix 5 by 10 if I don't apply the nonlinearity. The only thing is that this is not a general 5 by 10 matrix. It's a factorization into two smaller pieces. It's a low rank approximate. The rank of this is going to be at most 2 versus general 5 by 10 vector has matrix has rank at most 5. So even if in these sort of situations when you go to smaller dimension and a bigger dimension, if you drop the nonlinearity, you're going to do something non-trivial. You're going to be still linear, but you reduce the complexity of the parameter space. The parameter space is not going to be, so these matrices would have 10 times 5 parameters. So 5 by 10 is 50 parameters. Whereas this version has smaller number of parameters. How many parameters does this have? Let's see if people follow. If I do this procedure, how many parameters, like W1 and W2 together, how many like scalar parameters? Yeah. How many parameters a matrix, which is like 5 by 2 has? Five times 2, basically 10. 2 times 10, 20. The total number of parameters in this case is 30, whereas if I have a general, 5 by 10 matrix, the number of parameters is 50. So we reduce the number of parameters by a big chunk. Okay, so there is something going on even if you don't have nonlinearity. Okay. But usually people like apply these nonlinear. The output layer usually depends on whether you want to like, if you want to do classification, you've seen you can like absorb you can apply a sigmoid, get a probability, you can absorb the sigmoid into the loss, just leave it as logits. So this could be like logits or like probability, depending on whether if you apply the nonlinearity here or not. If we can apply the sigmoid here, for example, and so on. And the nonlinearity need not be sigmoid. It could be like any kind of nonlinearity. The common ones are ReLU, which looks like this. So it goes from 0 to a linear. So rectified linear unit, so 0 for negative values, and like that. The other ones are more perhaps could be popular. There's tangent hyperbolic, which what is tangent hyperbolic? It's like sine hyperbolic divided by cosine hyperbolic. So as x goes to infinity goes to 1, as x goes to negative infinity goes to negative 1, 0, it's 0, so it looks like that. So negative 1, 1. We can do other nonlinearities as well. But it shouldn't be linear. If linear, everything again would be linear. So these are neural networks, okay? Gives you parametric families of nonlinear functions. So if I have these nonlinearities, when I play with these W1 and W2, the shape of the function would change. And because the decision boundary is controlled by the shape of these functions, the decision boundary would change as well. It wouldn't be necessarily linear. So does that make sense? Neural networks. Very simple, kind of objects, composition of functions that are linear, fall interleaved with element-wise nonlinearity. That's basically neural networks. Okay, and if you do it enough, like more layers, it would be called deep learning. Okay, if you do 2 layers, it would be shallow network. The depth is how many layers you have. There are a lot more to deep learning, so there are a lot more innovations going on. But this is the basic one. So the one that I described, sometimes called multi-layer perceptron. These layers sometimes called dense layers, sometimes called fully connected layers. They're really like general linear maps followed by nonlinear. So MLP, multi-layer perceptron. So this is called like a fully connected layer, sometimes called dense layer. They're dense because all the weights are possible. I mean, if you set some of them to 0 ahead of the time, probably we get a sparse layer, but dense layer usually means like that. A cascade of these fully connected layers is called a multi-layer perceptron. Sometimes called feed-forward neural networks. Feed-forward. These are the basic classes of neural networks. Okay. How do you train a model? So this, and in the end of the day, at the end of the day, what you get is a function like this, where theta is a bunch of parameters, like W1, B1, W2, B2, W3, B3, and so on. And because these are constructed by composition of functions, so this is like equal to something like this, for example, it would be like rho W2, let's say, start from here. So W1 X plus B, B1, apply rho element wise, and then multiply by W2 plus B2, apply rho again, and then multiply by W3. The last layer, I can leave the nonlinearity out. So this would model a logic. So this could be like going anywhere in real life. So you can see that's like you have one hidden layer, 2 hidden layer, and the output layer. That it's like a two hidden layer setting. But you can see it's just a bunch of parameters in there. So it's parameterized by this sequence of parameters in our case. I can put it into the log loss, for example, I can do classification. So so log loss had like theta transpose X here, which was basically like W transpose X plus B here. I'm going to replace this with, so this was logistic regression, replace this with just this function, F theta of Xi. And then now argument over theta. Theta are all the parameters. Okay, so that would be going like sort of a maximum likelihood. So you can imagine that our probability model is like an extension of logistic regression, where this is sigma applied to F theta of X. So that's like implicit probability model. So do like MLE, it would reduce to doing the log loss because of the sigma. So I plug in F there, and in order to solve this optimization, but it's not going to be like convex anymore. It's not going to necessarily have a nice, unique solution. So implicit probability model goes to that, but it would be possible to do gradient descent on. And the reason why it would be possible is because gradient calculation follow the chain rule. So there's the chain rule of differentiation. So if you have two functions f and let's say g, let's say univariate, if I try to take the derivative with respect to t, right, you know how this works. So it would be like d dt of, so let me write this. Yeah, so it would be like derivative of the first comes out, and then there is a second evaluate of this guy, right? If you imagine like more general case, the derivative, you remember, is a linear map. This is just the coefficient of that linear map. In general, if you have this is like in R, like in general, if you have fg of x, you want to calculate the gradient, or let's say calculate the derivative. The derivative is really the linear form. This would be the composition of the basically the two gradients. So gradients are linear maps. You know linear maps. So the gradient of this evaluated basically at x, and then the gradient of this evaluated at g of x. These are two linear maps. You compose them basically matrix multiplication. These are two matrices. This is another matrix. We can go into this. It's easy to prove, but remember, so for a function, for example, the derivative at the point was, remember, this was the gradient, and then x minus x naught plus higher order term, or f like x plus. So we write it like this. X plus h is f of x plus gradient of f at x times h plus O of h. So this is really d h f of x. So the gradient of a function, no, not the gradient. So the derivative is really a linear map. So a linear map as a function of h. This is like the theta that you're looking at usually, like in linear maps. This is the coefficient. The coefficient is basically gradient, but the derivative is really that. If you imagine the derivative is like that, this generalizes to a generic function. So a general function, when you differentiate, has this linear expansion. So df at x applied to h. So this is really a matrix, which is called the Jacobian. The matrix of it has a name called Jacobian matrix. And if you have composition of two functions, basically the Jacobian or the derivative would be the composition of the two derivatives. If I haven't messed up the order. In any case, it's easy to calculate the gradient because each one of them is easy to calculate. So it's easy to calculate the gradient of this. And then once I have that, I can calculate the gradient of the whole thing by the chain rule. And this is called backpropagation. So calculating the gradient by chain rule is called backpropagation. Not going into much detail, so there's nothing much there except that you're calculating the gradient by using the chain rule. If you're interested, you could like work through that. But the main point is that I can do gradient descent. I can do we can do gradient descent. By the general standard gradient descent, the only complication is calculating the gradient, and gradient can be calculated by these chain rule. And PyTorch, for example, is written to do this chain rule calculation automatically. When you construct things and require gradient, it like tracks this chain rule basically. And once you're done, when you say like loss dot backward, it just follows that chain and calculates the gradient by passing through that chain. And calculating sort of the composition of the linear maps, basically. This part I don't want to spend too much time, but we can come back if we have time. It's just that it's easy to calculate the gradients of these. So neural networks are useful because it's easy to calculate automatically the gradient. And then you can do gradient descent or any first order method that uses gradient information. So we can do gradient descent or any first order optimization method that relies on gradients. Easy to calculate the gradient of NN by the chain rule of differentiation. And I'm going to write this like that. BFOG at X is equal to, if I'm not wrong, we want to be precise, something like this most likely is true. That's the result that you can actually prove easily. So derivative at X of FOG is the composition of the derivatives, which are linear maps. And so that's it. Okay, so we're not going to worry about how to calculate the gradient because PyTorch is doing it automatically. So you just construct your neural network, you construct your loss, do loss backward, and it just calculates the gradient of the loss with respect to your original parameters, which are like W1, W2, B1, B2, etc. Sounds good? So you're now experts in neural networks and deep learning. There's not much more. There's more, but that's the basic. Sounds good? Neural networks are clear. They're very popular because they're really easy to construct, and then you can be creative. Just like how many like layers, how many like nodes in the hidden layers. Can I cascade two networks, maybe one fully connected there, one fully connected down there, but then I do something at the here, add like one more layer there. So this, like if you have two networks, then this part is not fully connected because like these guys don't talk to these guys. But you can be creative there. Like the way to like cascade these is called the architecture of the neural network. There's a like great deal of work that people have done on trying to figure out what architectures work. But this is the basics. Okay, the basic idea is simple. You get a parametric nonlinear family of functions, nonlinear parametric family of functions that are easy to optimize over because the gradients can be easily calculated by the chain rule, which is called backpropagation. I can change my loss to like quadratic loss. I can do basically regression. Change it to log loss. I'm doing binary classification. If you do like the multivariate log loss or what we call cross entropy, and the output of this is instead of going down to here, let's say I stopped at this layer, that would be my output layer. So I can do tree-class classification because I'm mapping like input domain to R to the C. This goes into the softmax, produces class probability. So that replaces softmax regression. So softmax regression would be like theta, like S theta X. Now I'm replacing this part with F theta of X. But this is going to be mapping from input to like whatever number of classes. Softmax takes it and makes it into probabilities. So really, once you understand logistic regression and softmax regression, you can replace that linear part with this nonlinear function. You're now doing like nonlinear classification, binary or multi-class. Okay. Sounds good. Questions? I'm going to do some demonstration because it becomes much more clear once you see what like how these work. And like the beauty of PyTorch is like you can construct these and train them with a few lines of codes, and you can just manipulate them and see what happens. Questions, comments? So while I bring that up, you can think about questions. Okay, so let's go away. Yes, okay, anyway. Okay, so I'm going to increase the size a little bit. Too big maybe. Okay, so what I've written here is like this part is like function, which is already, I guess, uploaded on the GitHub. This just not a function, it's like a module, Python module. So it just collects some functions that load things. So load the MNIST data. This is our breast cancer data. So it loads the just call it. It would like read the breast cancer data that you've seen in your work problems into a pandas data frame, training indices. This selects the features, radius mean, texture mean, and diagnosis. Drops the NA columns, translate them into NumPy arrays, to NumPy. And then this one, just remember we had like malignant and benign, something like that for the classes of tumors. This turns it into a 0-1 class. And then we like basically select the rows that are trained in the X and Y, and then delete the rows that are trained to get the in the training indices to get the test data. So that's something that you can do. And then we turn each one into a torch tensor and return. So X train, the first argument would be like the training data, the X and then Y, and then X test and X and Y test. Okay, so that's simple. This gives you an n by 2 matrix of like for X's and n by 1 binary response. Okay, so we go here. I'm like importing that from loaders, import that load breast cancer that I wrote. And so this is just something that I use to test. This is not needed. So I'm going to do this. This is going to load. We're going to see that later. So and down there, we're going to load the data. So this is how you like you can define a simple neural network. So if you recall, we have this torch NN module that we import as NN. Torch NN functionals import as F. These are functionals like nonlinear functions, sigmoid stuff. So this defines a simple neural network. So we have a class. If you remember, like the convention in PyTorch is to drive these classes from NN module. So this is going to be our function, like neural network function. And this is a simple, like we call it simple net. You can call it whatever you want. It has a constructor. So here we initialize the object, and here the forward is just how we calculate the output. So basically the function applied to the input. So it takes the self, which is the object itself that's being created, input dimension, output dimension, and this has one hidden dimension. Like defaults are 1, 1, and 10. So it goes from 1 to 10 to 1. And this is standard. We're calling the constructor of the parent class. So I'm calling it like I'm not calling it a copilot's calling the FC1 and FC2, which is like fully connected 1, fully connected 2. We have created 2 linear layers. So these are linear functions. If you remember, input dimension to hidden dimension, and the hidden dimension to the output dimension. Okay, so it goes from 1 to 10, for example, and then 10 to 1. And then the forward pass, we're going to just apply them sequentially. Self that FC1, apply to the X is going to be our input. And then we pass the output of that layer through this ReLU. That's the rectified linear unit. That's one of the nonlinearities. This would like do that element-wise nonlinearity, and then we pass it through the second layer, which is a linear layer, and then we output that. Okay, so that's a very basic. Goes from 1 to 10 linearly, or like finely, and then nonlinearity, and then goes to 1. Okay, that's that basically defines like a univariate function from R to R via this 10 hidden layer. So if everything works, this should generate nonlinear functions. So if I ignore that part, maybe. Okay, I don't have that. Let's create. say model equal simple net. So if you do this, you can see it has these two layers. Oh, let's do it up here. So here, so it has these two layers. Like create 100 points in maybe 5 to 5. Okay. So if this works. So this creates like a vector size 100, and then reshape -1 and y is so without this, so the dimension of this is going to be at you can see 100 by 1. Without this, it would be just 100. So it reshapes it to whatever dimension is needed here, and then 1 will be 101. Because like the convention is like if you follow this convention, things would you like less likely to run into errors because you operate on each row. If it doesn't have a row, then broadcasting happens and like crazy things. You might just spend like an entire day debugging what happens. But this is a good convention to have. Like even if your data is one-dimensional, do it as a matrix, like 100 by 1, and then it operates on the rows. Otherwise, it tries to like do some broadcasting and you run into hard to find bugs. So this already understands that it needs to do that. Like plot. So I'm going to call this like y, let's say, model x, plot x versus y. Okay. Okay, so you got an error, cannot call numpy on tensor that requires graph. So this is not going to be good, but attach numpy. Let's see if I recall correctly. Okay, so you had to like detach it and then from the gradient, so calculation, and then turn it to numpy. Now you can see this is one function. Okay, these are linearly, like when I create a model, it just randomly initializes the weights. So if I run this again, because I initialized the model, it's gonna regenerate another. So there is a bit of nonlinearity, as you'd see. So these are like nonlinear functions. ReLUs are, if you think about this, the functions that you get out of this have to be piecewise linear. There's like a little math problem because ReLUs are piecewise linear, and everything in between is linear. You get piecewise linear functions. If I reduce the hidden dimension to 2, probably you would see like more like the nature of the piecewise linear. So like you see these kinks. So it's like piecewise linear. If I increase the number of hidden dimensions, it's harder to see, like 50 dimensions. Starts to look like smooth. It's not smooth, but it's just, you get these crazy shapes. Okay, so these are like randomly generated weights. So these are different weights. So this describes like as you generate them randomly, you observe different like nonlinear functions. So these are your class of functions that you try to find. So for example, if you doing univariate classification, and if let's say this is the logit. So if this is my model, this is going to be the logit. So I'm going to do like, for example, torch sigmoid. So let's see what it would do. So that would be like a classification function because I'm passing it through the sigmoid. So this is now a probability, let's say. So you can see it's like the decision boundary, let's say if it's 50, it's going to be like anything above it would be like class 1, anything below would be class 0, so it would be like anything in this interval would be class 1, anything outside would be class 0. So you achieve like non-linear boundary. Linear boundary here would be like a single point to one side is one class, to the other side is another class. Okay, sort of clear. Okay, and then questions. Here sort of is another like version, which is a little bit cleaner. So we have a dense, define a dense layer. Just dense, you can call it whatever you want. Again, from the class and the module, this just defines one of those layers. So it has one fully connected layer, which is linear, input dimension, output dimension. And then I also pass it an activation. So this would be a function. Here for default, I'm passing it tangent h. And I'm going to store that function here in the activation field here. So like the property. And when I'm calculating it, I apply the fully connected layer and then apply the activation. So it's just linear followed by element-wise activation. So this defines one of those layers. Now I can like generate different layers and then concatenate them. So this you can do easily by this sort of NN sequential without like doing much. So NN sequential takes like a sequence, like a bunch of these modules and just compose them. Okay, so passes it. So this is going to be a new model, which is another like one of these guys. The forward pass of it basically is going to apply the forward pass of this first, and it feeds the result to the forward pass of this, and the forward pass of this, and the forward pass of this. So basically you get function composition. So we're composing like first apply this from 1 to 10, and then 10 to 5, 5 to 1, and then apply sigmoid here at the end. So this is really a probability model. Then I can try to plot this as well. So here, for example, this is one of the functions that I get. Okay, so this now has like more than one hidden layer. So one in here, 2, and then output layer. So it's like 2 hidden layers. So you can run it a couple of times. Like by chance, this looks like very much like a linear, that's not linear, but linear boundary. They can see like you get crazy functions as well. Okay, sounds good. So how do we now train these? Now here I'll load our breast cancer data. You would have the train. So this part is like the idiosyncrasies of PyTorch, because if the data types don't match, so one of them is double, the other is float, then you get into problems. So you turn everything into float or double. Let's say float, because the default, I guess, is float. So returning the data type into float, and then VU minus 1 and 1 is like, as I mentioned, so these are like vectors, you turn them into like a matrix by 1. So minus 1, you reshapes it. So this VU is like a reshape, but it doesn't copy the data. It's the underlying data is the same, you just view it in a different shape. So for example, if you have like a 10 by 1, okay, so let me show you what this does. It's easier. So actually we don't have time. Next time maybe I'll show you. But this like you can say, for example, -1 and 2, it would make it into whatever dimension needed by 2 so that you cover all the elements. So if you had 100 elements, it would be by 50 by 2. Here I have like 100 elements, so it would be 100 by 1. But it has going to be having 2 dimensions. If you don't do it, you run into very interesting errors. Not errors, but things blow up, and it's hard to figure out what's going on, because the model is like doing something. Try to do it along the rows, but there are no rows, so it extends along the rows. And in any case, so I have that. I have like constructed the model because the input is 2-dimensional, 2 to 10, 10 to 1, and then sigmoid. So that's my neural network. Okay, and let's plot the decision boundary. So this model, this is the function that I wrote before. These are the data. You can see the decision boundary. Multiple. Let's do it multiple times. These are the level sets, and you can see it's sort of non-linear. So this part is class 1, the rest is class sort of 0. So by the contours, you can see like you get interesting shapes, not necessarily a couple of times. The classes are like not linear. So this is sort of linear by accident, but you can get crazy. Yeah, so you get the idea. So how do we train this? So I'm removing the last layer here, so the sigmoid, because I want to apply the log loss, so absorbing this into the loss. So now I create this 2 by 10, 10 by 1. You can list the model parameters, and I have my loss, so it takes the model. This part can be simpler, so let me just simplify it. Just X train that we have, and then we have like Y train. So this is the log loss. So the only thing that's changing is the way I calculate that those lodges model applied to X train. It applies it to every row. I get those lodges, and this goes into the log loss. Okay, that's, if you recall, the linear model that we had is just the model was linear before here. And then I wrote like a train function that like contains our previous like gradient descent. So so this does the gradient updates that we like did. If I don't like specify the optimizer parameter here, it uses our like SGD, and these would just be the steps that we followed before. Okay, it's not something fancy. If I specify the optimizer, it's going to choose that optimizer. And here I just want to compare our own. So this is just a like repackaged version of the loop that we saw before. So you can see like the loss, I pass it the loss function, applies it to the model, and the loss function applies the loss function to the model. This does the gradient calculations. This does the gradient at the step. This zeroes out the gradient and it collects the loss. So all of this should be clear. It's just that we're parametrically passing the model the loss function, and by the end of this, the model parameters are updated. This step is going to update the model parameters. How does this know what parameters to update? It knows it because when we construct it, we pass it the model parameters. So there's a pointer to that. And okay, so let me show you what it does. You can see very simple, like there's nothing much here changed from linear to nonlinear, except the definition of the model. Now, if I run this, I'm doing 2000 steps. In like learning rate this, momentum that. Let's see if it works. You can see like it starts to go down, and like loss is 0.40. Here I'm going to wrap it into a sigmoid. So this is the wrap model. This model is doing the logit. So now I pass it through a sigmoid. This is going to be probabilities, because this plot decision boundary that we wrote requires like a probability model. So I'm not going to plot this. So if I plot this, so you'd see like a nice like non-linear boundary. Okay, it's close to linear, but it's not linear. If I do the everyone's favorite, so this is a very popular, this so-called Adam optimizer. A few years, it's like a few years old, but like impressive performance. So this requires, like in this case, I can increase the step size to like 0.01. Number of steps I don't need as much. So I think this is already there on the GitHub. You can play with it, and you can see like it converges much faster. The loss is sort of the same 0.39. So this is impressive because this we wrote ourselves without that much work. But what I want to show you is the output, and this is what it learned. Okay, and a couple of interesting things to note is this is a different function. It's a different decision boundary, and it's much sharper. I don't know why this is, but oftentimes the things that this learns is much like sharper transition. So if you look at, we can calculate the, just give me a second. We can calculate this is the prediction of this model on the test data. So you can calculate it's like 0.87 accuracy. Our like less fancy optimizer produced got it. The training loss is 0.40. The training loss, you can also like calculate the test loss, which is like log loss. Log loss is like a surrogate. So this is our like not so fancy optimizer, but you can see the it's actually the way I cooked it up. The test accuracy is slightly better. So 0.9 for the other one, 0.787. So the same neural network fit to the same data, you get different functions or different decision boundaries, different looking decision boundaries, similar looking, like 0.80, between 0.87, 88, 89, 0.90 is the limit of this problem, sort of, it seems. So all of these are approaching that. And also logistic regression gets close to that, like 0.89. If you recall, the Nadaria Watson also produced something like that. So you can get different decision boundaries, almost like similar performance. It's hard to tell which one is better. If you like nonlinear boundaries, you can go with that. If you like Adam optimizer, you can go with that. This is the difficulty of model selection. So I think stop here. I'm going to post this. You can play with it. You might get like, try to change the number of layers here, like do other crazy stuff, see what happens. And if you really engineer, you can try to overfit to your test data. So you can try to engineer to improve like your test error, but then someone else comes up with like the rest of the data and you're not necessarily going to do well. So if you try to like optimize over the test data, it's not going to work that well. Okay, thank you guys. See you next time.